Hello, George Romanis here. In previous video, we estimated the number of atoms that hit that wall every second of our lives. In this video, we can ask ourselves, what is the average speed of atoms in air around us? To answer that question, we will use amazing concepts of kinetic theory of gases and Maxwell-Boltzmann distribution of speeds. Let's start. Maxwell-Boltzmann distribution of speeds was that f of v is equal, we had this square root of m divided by 2 pi kt to power 3 times 4 pi v squared times e to negative mv squared divided by 2 kt, where m is mass of particles, k is Boltzmann constant, 1.38 times 10 to power negative 23 joules per Kelvin, T is absolute temperature in Kelvin, and V is speed. And you will kindly remember that this function has the following shape. If here is V and here is f of V, probability density function, then it's positively skewed, which means it might look something like this. And because skewness is positive, mean speed or mean value of this variable, in which case we have speed as the variable, is not the most probable. This is the most probable, V most probable, but mean is shifted to the right because distribution is positively skewed. You will also remember that we discussed if this is the curve for temperature T1, if we are interested for some other temperature T2 that is above temperature T1, the curve might look, use dot dash line, might look something like this. And this is for temperature T2, namely the peak is lower than for lower temperature, but it's shifted to the right, which means there is higher probability of finding faster atoms in hotter gas. At any rate, the goal of today's video is to find this value of average speed in a gas. We will recognize that this distribution is continuous distribution. And therefore, we know that average, in that case, is simply equal integral over the entire distribution, and in this case it is 0 to positive infinity, of v times f of v dv. That is mean value of a distribution. Now, the rest of the video is enjoying beautiful mathematics of solving integrals. Average v is equal, 4 pi, this one, times square root m divided by 2 pi kt to power 3, that's constant, and then integral 0 to infinity. This v squared will combine with this v, giving me v cubed, e to negative mv squared divided by 2kt dv. How do we solve this integral? Well, we introduce substitution. Let us do it here. And substitution will be that v squared, not v cubed, v squared is equal k. Some of you might say, but how do you know this? How could I figure this out? You can't if you don't study mathematics and read books on that. Smarter people before me figured out how to solve this integral. I follow their steps and now I know how to do it. I know that if you have this dependency between this variable here and this over here, then this is the substitution you need to introduce. That's why you study things. At any rate, from here you will notice that you have 2v dv equals dk. Or from here we can write that v dv is equal dk over 2. But now I will multiply this with k, and notice that I will get here k times v dv is equal k dk over 2. But k is v squared. So really left side is v cubed dv is equal k dk over 2. Now it's clear for you why substitution had to be this and not something else. With this, we go back here and we attempt solving this integral that I will call I. So this integral I becomes integral, limits in this case stay the same, 0 to infinity, v cubed dv is k dk, and I have this e to, let me call m2k over t some constant a, and v squared is k with minus. Now this, of course, we can write it a little bit. Oh, and I forgot over 2. We can write this a little bit nicer as 1 over 2. This is constant. We take it out. Integral is 0 to infinity k e to negative ak dk. Now, how do we solve this integral? Well, this integral we solve using integration by parts. We know that integral of f dg in terms of integration by parts is fg minus integral g df. In this particular case over here, I will say that my function f is equal k, and my function dg is consequently e to power negative ak dk. From here, df is equal dk, because I need df here, and I need g. G I get integrating this, but this is table integral. If you don't know it, then, study. This is negative 1 over a e to negative ak. Now with this, and this, I use this formula to solve that integral. In other words, my integral I becomes this 1 over 2, and then I have f times g. F is k times g, and that is negative 1 over a e to negative ak. And that needs to be evaluated between 0 and infinity, minus integral between 0 and infinity g, but g is negative 1 over a e to negative ak times df, but df is simply dk. Well, now we need to solve this limit over here. So limit when k tends to infinity, let's first go to the upper limit of this integral of, what do we have here? We have this k divided by a and then divided by e to ak. Instead of this negative, I put this downstairs, and I'm not interested in this negative sign. Who cares? If k tends to infinity, this is infinity, and e to infinity is infinity over infinity, and then therefore we use L'Hopital's rule that says that this limit is equal limit when k tends to infinity, take derivative of this, and that is 1, and take derivative of this, and that would be a squared e to ak, and this is equal, now when I evaluate this limit, nominator is 1, but the denominator is still infinity, which means this limit is 0. Now if I evaluate a limit when k tends to 0, that's the lower bound of this integral, of k over a e a k, that is, what do we have? When k tends to 0, this is 0, and when e to 0 is 1 times this a, at any rate, this 0 divided by some number, that ends up being 0. So we can see that this term altogether is 0. 0 minus 0 is 0. Which means that our integral I is equal 1 over 2, negative and negative will give me positive, and this a I can bring in front of the integral, so I get integral 0 to infinity e to negative ak dk. But this is once again table integral that we already solved here, so I will get here that this is negative 1 over 2a squared e to negative ak in the limits between 0 and infinity. Well, let's write it. Ak in the limits between 0 and infinity, and this will be negative 1 over 2a squared. I will have 1 over e to infinity minus 1 over e to 0, and of course this tends to 0, and this guy is actually 1, because e to 0 is 1, which means that my integral I becomes simply 1 over 2a squared, because this negative and this negative will cancel. But you will remember that a was m divided by 2kt, which means that the integral I is equal 1 over 2 4k squared t squared divided by m squared. So this and this cancel, and I will get that this is 2k squared t squared divided by m squared. And now going back all the way to this expression over here, we found integral I have to multiply that result with this factor over here, which means that the average value of speed of atoms at temperature T is equal 4 pi square root m divided by 2 pi kt, and times this solution of our integral 2k squared t squared divided by m squared. And of course we can organize this to look a little bit better. This is to power 3, and if you do that, that is very simple mathematical manipulation. You will get that the mean speed of atoms is equal square root of 8 kt divided by pi times m. Absolutely beautiful result, because we notice that by knowing macroscopic quantity of the gas, namely temperature, and mass is all we need to find average speed. Here we have a nice table that shows you the beauty of this equation, because I calculated mean speeds for different gases: hydrogen, water vapor, nitrogen, oxygen, carbon dioxide, and radon. Except radon, these are gases that you breathe readily in your room, sometimes maybe even radon. And calculations are carried out for room pressure of 1000 millibars and room temperature of 23 degrees Celsius. Masses of these atoms are given here, and their diameter in angstroms is given here. If you want diameter in meters, here is relationship between angstrom and meter. Mean speed of hydrogen in your room is 1700 meters per second. Water vapor is flying across your room with the speed of almost 600 meters per second. Nitrogen and oxygen are similar and somewhat slower. Carbon dioxide is yet slower, and radon is even slower. Why are these slower? They are slower because you can see I align them in terms of their masses. The heavier they are, the slower they move. Today's video helped us visualize what is happening in air around us. Now we answered question how many atoms are hitting wall behind me in my previous video. Today we saw what is the mean speed of atoms in your room and my room at 23 degrees Celsius. Now it's time to tackle another question. And that's what's the most likely, most probable speed of atoms in your room and my room. Well, you saw that this distribution is skewed. That means that the most probable speed is not mean speed. And that's a very interesting question indeed, because if you were to pick a random atom in your room or my room, what would be your best guess for speed of that random atom? That's what we are going to explore in next video. Until then, goodbye.